So let's look at some other potential examples. We're going to start again, just one more review. This is the same slide we've been using. A volume charge density here. We're finding the potential here. These are the vectors that you're used to. This goes to the source point. This goes to the field point. This is the difference vector. And this is your dq. So if you put that into dV is k dq over r, which is a generalization of a point charge potential, and then integrate over the charge density. That gives you the general equation for the potential at the position r. So here's the r dependence right here, and realize if you integrate over the prime variables, this quantity here has no r primes in it. And like we said before, you can extend this type of charge density to a surface charge density or a line charge density. Well, we're going to take another finite line element. We'll do the simple case first, where we look at a position that is along the z-axis and where we put the line elements in a symmetric form about the z-axis. So it goes along the x-axis from minus L to L. The charge density is lambda and it's uniform. As I said, we'll use this equation here, and we want to define r prime, we want to define r, and we want to define dl prime. So realize that if we have lambda constant, then this is replaced with just a constant lambda. So here's our dl. It's a dx, and I'll put a prime on it. So there's a dx prime here. If we look at the vectors, r prime is this vector here. R vector goes up to our field point, and then here's r minus r prime. What we're interested in is the length of that vector, so we'll establish that. And here's the translation of all these vectors. The r prime vector is x prime times x hat. R is z hat. The difference between these two vectors is this. This is r prime, this is r. The length of that vector is x prime squared plus z squared to the 1/2 power, and then dq is equal to lambda, which is a constant, times dl prime, which is lambda dx. And that holds up for x between minus L and L, and lambda is a constant. Here's our integral, and so we want to put the translation values into the integral. Lambda is a constant, so k lambda comes outside. We've determined what r minus r prime magnitude is, and here's our dx to go with the lambda to give us our dq. If you integrate this, you end up with this expression right here. So it's a ratio of this square root factor here plus L, this square root minus L. So let's look at the integral in terms of using Mathematica. So here's the integral, here's the answer right here, and then this is where we take the ratio of this divided by this because we have minus log here. So we get the same answer we have up here. What does it look like? Well, it blows up at 0 because this goes to 0, this goes to L, so you have a L minus L. So that's why that goes berserk. As you move away, it falls very rapidly, and then you have this slow decay with z. So we're looking then at the potential as we go along this axis away from the line charge. Here's the integral obtained by Mathematica and the plot. So this right here is the code to produce this curve here. Well, what's the field? So we go back to our results. Here's our potential, and it's a function of z only. Well, we've already shown that E is found by taking minus the gradient. Let's just do it. I'm lazy, so I'm using Mathematica, but it's basically just differentiating this function here with respect to z. And what you get is a vector 0, 0, and here's the z component only. And you can see what it looks like. There's no dependence up here. Down here there's a z, and there's a z inside the square root. Now why we can do this is because of the symmetry of the problem. If you take a look at what we've got this and this. Every little unit here has a corresponding unit here of dq, so that up here the x components cancel. So we have fields, I'm not drawing this very well, but these are the fields, and so the x components cancel and we're only left with the z component. So along this line, because of that symmetry, we have only a z dependence. If we only want this along the z-axis, so this would be Ez, the z component as a function of z, we'll get this value here. Let's look at this in terms of brute force. We've done this before. If you go back to the general equation for E, it looks like this. So you have this right here is r hat, this is k lambda of r prime, and then here's your distance squared. So that's what gives you the E field for a line charge in general. Well, we did that problem, and so when we finished we had E on the z-axis, and again remember this is only holds because of symmetry, and it only holds on the z-axis, and this is what we got here. You can see that it's the same. This is the z component and they're exactly the same. So brute force, or coming at it from the potential where we derive the potential, we get the same E field as we do if we do it brute force. I just want to point out that if we plot the value of E sub z, this is the function that we get, so that's this function right here. And what I've done is I've taken minus the v of z. Now the slope of this curve here is equal to E of z, and that's why I put the minus sign in. So here you have very, very high slope. In fact, it would go to infinity if we got closer and closer. And then as you go up, the slope decreases, 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 and approaches 0. And so that's what you see here. The E field is in fact the slope of this function here with the minus sign. Well, what happens if we go to an infinite line charge? We already have this finite line charge, and so it seems like if we just let the L values go to infinity, remember this is minus L to L, so if we let L go to infinity, the line charge goes in both directions. We should be able to get the potential due to an infinite line charge. So suppose you have L much larger than Z. The E field behaves, because if you take that limit, so you take the E field and let L get very, very large, then this is the result that you get. We drop the Z squared because it's much smaller than L squared. Well, that's this one right here. This Z remains right here, and so there's an L here. It cancels this L, and so this is the E field on the Z axis, and that's well known and easy to derive with Gauss's law. The potential is not so easy. It's not well behaved. And the reason is because of this denominator. If you let L get very, very long, you'll have L minus L. It's going to blow up. So the potential blows up if we let L go to plus minus infinity. If you remember, our V calculations assumes a reference point, usually taken as 0 potential, and it's occurring at infinity. Here we have to assume a point at a finite distance, say z equals z0 as our reference point, such that for convenience we let that be 0. Keeping z equal to infinity as the so-called big reference point in the sky, we would write the potential at z minus v of z0 is equal to, now get this, we're going to use the infinity potential for this term here, and we're going to use it again for this term right here. So we have this quantity here minus what looks the same except for that 0 there. Well, the two infinities cancel. Sneaky, isn't it? So these two cancel, and we're left with the value of v of z minus v of z0. We're using this trick in order to get the potential difference between these two values because we want to use this equation to write that down. So here's how we do it. So here's our expression, and so we take the potential difference. First we write that out. So here we have the first term, that's at z. The second term is at z0. Well, you've got two logs here, both times k lambda, so we can bring that outside. and then the two logs with the minus sign becomes a ratio. And so that's what I have here. So if I now look at both of these, they both blow up. We're not done yet. I'm going to save you a lot of pain, but if we rewrite this whole thing in terms of z over L and z0 over L, so we factor out those terms, this is what that difference looks like. It looks like k lambda times these logs here. So each of these terms represents what you see here. If I rewrite it in terms of taking out these squares, I get a 2 times the log of these factors here. So what I've done is I've taken the squares right here. So I'm only taking that first term. That's why the 2 comes out. So when I'm done, this is 2k lambda times this function here, which is finite. So that's what I mean by using this trick, using the results of having v at infinity, which, remember, gives a blow-up of those terms. But if we take the fact that we're subtracting these infinities, what happens then is that you get a finite difference between the vz and the v0. This whole thing is called renormalization, and it saves high-energy physics many, many times in terms of the way they calculate fields and so on. Keep that in mind, that it's a very sneaky trick, but it works. If we go back to cylindrical coordinates, so we now write this in terms of a s vector, and then we put z along the axis, we can write the E field in terms of this s vector, and it's pointing in a direction normal to the surface. And so every point on this circle would have a normal, so that would be s hat. And the value of the field at that point, 2k lambda over the distance to that point. If we take the equation that we just developed, the potential for an infinitely long wire at S minus the potential at some S0 is equal to this quantity here. So this is the equation we developed by using our trick. Now I might mention that if you keep the S0 as is, you can factor out a term that will involve log of S0 and then minus the log of S. If you do that, you can let log of S0 be a constant. So sometimes you write this expression in terms of a constant rather than put in the S0 in the log. Well, this is what it looks like. I've plotted 1 over S, which is the field, and that's this right here. So this is how the field falls. This would be the S component because that's all we have. So it's this vector with this quantity plotted. So the magnitude of E is this one right here. Here's log 1 over S, so I just let S0 be 1, and that's this quantity right here. And right at this point where it goes through 0, that's equal to what we call S0. We can put that anywhere we want. I chose it so that the value of the potential is equal to 0 at that point. But notice it goes negative. If you take minus the slope of this curve, you'll get this curve. Minus the gradient of the potential will give you the field. For the v as given, you take the gradient of v, and so in this case here, because it's a function of only one variable, you'll take the s component of the gradient, and the first term of the gradient in cylindrical coordinates is just the first derivative. So when you take the derivative of that, you get 1 over s. If you take the slope of this curve with the minus sign, you'll get the field 1 over s. So next time I'll try to do some additional examples.